Welcome to a video on curve sketching part 3. The next two examples here I'm going to do are doable by techniques from advanced functions. You will not need to do calculus techniques on these examples. However, I'm going to discuss the full algorithm with both of those examples so that you get the sense of how the algorithm works. So this next example is a piecewise graph. And here's the full algorithm for the calculus class that you could apply to any type of graph. So first of all, taking the derivative of the quadratic here, we'd have a linear, and of this rational function, we get another rational function. Notice how the equal to 2 is not included here because we can't include it unless we've proven that it's a smooth slope at x equals 2. And then here's our second derivative because we will need it. I have it down below. So start off with the usual, looking at the original function. There will be no holes. The y-intercept is at -1. X-intercept here would be at plus or minus 1. And both of these are in the domain because both of these are below positive 2 here. And then the second piece doesn't have any values that would make this whole thing become 0. There is a VA in this equation. The second piece has a denominator, so x cannot be 1. However, this VA is actually not part of the domain for our piecewise graph. So there are no domain restrictions for this equation. Okay, now on to the end behaviors. In terms of the asymptotes that we could have, because we do have a rational piece, we will have actually a horizontal asymptote. You should recognize this. This is from grade 11, rational function, parent function that has a vertical stretch and a shift to the right by 1. You've learned in advanced functions that if you have a horizontal asymptote, then there will be no oblique asymptote. So I'm going to do end behavior without using formal limits. Just very quickly, I will say that as x goes to -infinity, y goes to positive infinity. This is because on the left piece, this is a parabola that opens up. So yes, the y will go completely up on that side. On the other piece, when x goes to positive infinity, y will go towards 0 because this is the piece on the right side, and this is a rational function that doesn't have any shift up or down, so you will have a horizontal asymptote at 0. We will skip for now these two steps. We've done it with the previous example. Moving on to this first derivative, which is found right there. We're going to start by looking at critical points from the numerator to see if there are any horizontal tangent points. So numerator of the first piece, well, we have 2x. That is obviously equal to 0 if x equals 0. And we can find the y value of this point by taking 0 and putting it back into the original. 0 matches to the very first piece, so 0 squared minus 1 will give us -1. And so this first critical point is 0, -1. In the second part of the first derivative, we have potentially x equals to 1, where the derivative does not exist. But this x equal to 1 is not part of our domain. Lastly, this derivative does not have x equals 2 included, because potentially there's a sharp point there. So that's also considered one of the critical points. And so that's summarized over here. X equals 1 is not in domain, so we ignore it. But x equals 2, we have to look at it. What happens there? Is it a sharp point, or is there a jump discontinuity? We don't know until we do a check using continuity definition. Here it is. So continuity at x equals 2. We have to have the output at 2 equal to the what the function approaches on the left piece, and also equal to what the function approaches on the right piece. Well, plugging in 2 into this piece, we have 2 squared, which is 4 minus 1 gives us a 3. And when we put 2 here, 2 minus 1 would be 1. 3 divided by 1 is also 3. So these two things are equal to each other. F of 2 itself, well, that is together with the second piece, so this is already accomplished by this check. So the pieces do connect, and they connect at this 2, 3 point, and we're going to consider this as a critical point because potentially there could be a sharp point. We're going to skip these 2 steps here with stars. We're going to do it in a different way than we did the prior example. Moving on to the second derivative, which was found over here. Possible inflection point could be when the derivative is equal to 0. Well, this first piece is never 0, and the second piece doesn't have x in the numerator, so that one's never 0. We can have x equals to 1 again, where the derivative or second derivative would be undefined, but again x equals to 1 is not in this domain. So the only potential possible inflection point is again this x equals to 2, because that's where the second derivative is undefined. What we're going to do now is find the concave up and concave down intervals. We're going to take this x equals 2, which is the only possible inflection point, and put it into a number sign or number chart. And we have y double prime is always going to be positive. Why? Well, if we take values that are lower than 2, for example 0, and we plugged it inside here, well, there's nothing to plug here. It's always positive 2. And on this domain, x's are greater than 2. So on this domain, we have always positive. So this side right here, we use the first piece of the second derivative. This side right here, we use the second piece of the derivative. In any case, it's always positive, or the output here of the function is always concave up. Then we decide which of these, or is this an actual inflection point? And the answer is no, because it does not change concavity there. Then I'm going to show you how to classify the critical points that we found over here, the x equals 0 and x equals 2 point, using the second derivative test instead of the first derivative test. So let's start off with x equals 0. We know that this critical point came from the numerator of the one of the pieces, and so it had a horizontal tangent there. The second derivative at 0 would be in this region over here, and it is concave up here. So if you imagine we have horizontal tangent in the middle, but then it's always concave up, that you could visualize that to yourself, that is going to be a minimum turning point. Next, critical point at x equals 2. First derivative at x equals 2 will be undefined. We need to prove this. We cannot just assume that. So I have here a comparison of 2 things. Recall, we did this already. Continuity at x equals 2 definition was using the original function, limits on both sides, as well as the point itself. For smoothness, we want to use the derivative pieces, and we want to check whether slope from the left equals to slope from the right. In this case, it does not. So we do know it's going to be a sharp point. So next, what we're going to do is plot all the points that are in yellow. So that's the 2 x-intercepts, and the 2 critical points are plotted. And we can add in our end behavior pieces, that it goes to infinity here and to 0 on this side. We can finish off the graph right now. We know everything is going to be concave up, so we can join each piece. I have noticed that I made a mistake here. I should have said maximum sharp point. Let's talk about it. Here it was minimum turning point because we had a flat slope, horizontal tangent, and then concave up. Here we had undefined slope and concave up on either side. So it should have been maximum sharp point as it is seen from the graph that we've already done.